Hey everyone, and welcome to today's Explainer. Today we are taking a really fun deep dive into Lecture 10 from Skip Uni, and we're focusing entirely on C++ constants. We're going to unpack this fundamental concept and see exactly how it enforces some pretty strict rules for data security and memory management. Let's get right into it. So, quick question for you. What happens if you accidentally change the speed of light in your code? I know, it sounds kind of crazy, right? But imagine you're building this massive physics engine or some complex scientific simulator. In the middle of millions of lines of code, a tiny glitch or just a stray line of logic accidentally overwrites that fundamental universal value. Well, your entire simulation crashes. Your results are completely invalid. This catastrophic hypothetical scenario perfectly illustrates exactly why certain pieces of data absolutely must be protected from change. All right, moving on to Section 1, the sealed bag analogy. To really ground this, think of a normal variable, like an open bag. You can freely toss your laptop in there, swap it out for a water bottle later, or just throw in a pen. It's completely fluid. The contents change constantly based on whatever you need at the moment. But a constant? That's like putting a single pen inside that bag and literally slapping a padlock on it, sealing it shut. Once that item is in there, it is locked. It is entirely fixed. You can't remove it, and there's no way you're replacing it with a water bottle later down the line. So how do we actually go about sealing this bag in our code? Well, we use the const keyword. When you apply this qualifier to a variable in C++, you're essentially sealing the container. You are telling the compiler, listen up, whatever value I assign to this right now, do not ever let it change, no matter what happens later in the program. Let's look at Section 2, why fix data values. The answer really lies in real-world applications. When you're writing complex software like calculating physical movements in a video game engine where you need the exact speed of light, or maybe you're doing heavy mathematical computations that rely on the exact value of pi. Or think about machine learning algorithms. They have a learning rate, usually called alpha, that dictates how the model actually learns. These are universally fixed values. A single accidental modification to any of these during runtime could literally break your entire application or just completely ruin your machine learning model. The crucial takeaway here is that declaring constants provides this incredible, impenetrable layer of safety for your application. You are guaranteeing that these critical values remain completely unchanged throughout the entire execution of the program. It totally removes the human error factor. You don't have to stress about a teammate accidentally overwriting your learning rate 6 months down the line. So let's look under the hood in Section 3, constants in the memory. Let's start with this number, 4. When you declare a standard integer variable in C++, the system actually needs to make space for it. Typically, it goes into your RAM and allocates a 4-byte memory block for that specific data. Just imagine a little 4-byte box sitting right there in your computer's memory waiting to hold a number. When we compare the memory behavior between the two, we see a pretty stark difference. With a normal variable, let's say we declare int b equals 20. That 4-byte block gets the number 20. Cool. On the very next line, we write b equals 30. The system happily overwrites the 20 and just replaces it with a 30. No problem at all. But for the constant, if we declare const int a equals 10, the system allocates that 4-byte block, puts the 10 inside, and then puts a strict permanent stamp on that memory block. If we try to write a equals 30 on the next line, the system completely rejects the overwrite attempt. The value is locked down. The compilation simply fails.
Which brings us to Section 4, the golden initialization wall.
Because memory is locked down so fiercely with constants, C++ enforces a rule that is actually a really common trap in technical interviews. Let's establish the baseline first, though. With standard variables, the compiler is super forgiving. In step 1, you can just declare the container first, like int a. You're basically just telling the system, hey, do me a favor, reserve a 4-byte box for me. Then, in step 2, completely on your own time, maybe 100 lines of code later, or maybe after waiting for a user to type something on their keyboard, you can finally assign the value, like a equals 20.
But here is exactly where that strict rule comes into play. If you try that exact same flexible two-step process with a constant, you are going to crash straight into a wall. If you write const int a on line 1, trying to just declare an empty sealed bag, and then on the very next line you try to assign it with a equals 20, boom. The compiler immediately throws a hard error. You literally cannot seal an empty bag and then try to pry it open a second later to stuff a value inside. And that brings us to this definitive quote from Skip Uni Lecture 10. A constant must be initialized at the exact time it is declared.
I really want you to lock this strict requirement into your memory right now. The absolute moment you type const, you've got to use an equal sign and assign its permanent value on that exact same line. No exceptions, no delaying, and absolutely no waiting for user input. Declare it and initialize it simultaneously. That's the whole shebang. Which leaves us with this final thought. Now that you understand the mechanics of the sealed bag, and you know exactly how to lock down memory to prevent catastrophic overrides, I want you to look at your own projects. Which vulnerable variables in your codebase are just sitting there in open bags, completely exposed, waiting to be accidentally changed? Which ones are you going to seal up first using the const keyword? Take this knowledge, apply it to your code today, and build safer, more reliable applications. Thanks so much for joining me on this explainer, and I will see you in the next one.
Welcome to Start Studying. Don't forget to like and subscribe.